With that, we'll move on to the first paper. The first paper is entitled Simulation of Adsorption in Model Microporous Graphite and is presented by Dr. Nicholoson from Imperial College.
Thank you. I can have the first slide. What I'm going to talk about today is simulation using the grand ensemble. It's in there. The work I want to talk about is simulation using the grand ensemble technique of a model for microporous graphite. And two things. First of all, I want to show how the system can be characterized using data from adsorption on plane surfaces, and then to look at this particular model. Next slide. These are the systems the adsorptives that I've been looking at, argon and nitrogen, and those are the main parameters. The things to notice here, the argon interaction is much stronger in argon than in nitrogen, but the nitrogen molecule is much bigger than the argon. The other parameters here, the lambda and the Q, are ones which I'm not going to have a lot of time to discuss, but they are ones which I've used to adjust the adsorbent potential to optimize plane surface absorption. Have the next slide. This is the isotherm for argon on the plane surface of graphite. These are the experimental data, the crosses there. And you can see that by adjusting these two parameters, by fine-tuning the potential, you can get quite a good agreement over this very sensitive region where there's a transition between a liquid-like state on the surface and a solid-like state in this region. Next slide, please. For nitrogen, the Leonard-Jones model is, of course, not so satisfactory. The experimental data, again, shows a transition in this region. The nitrogen, of course, is now commensurate with the graphite surface, which is different from argon. And the simulation does show the transition here from a liquid-like state to a solid-like commensurate state, but it's much sharper and it covers a wider region of theta. But do notice that this is a very narrow range of theta which I'm examining on this scale. Next slide. And here are some details about the core model. The basic model is one in which I'm looking at slit-like pores with graphite 001 surfaces separated by integer multiples of the graphite interplanar spacing. That's this quantity D here, and you can see that that's the value that I've taken for D. So H here is the distance between carbon centres. The pore is in the middle of those two carbon planes, and H prime is the space that the molecules can get into in the model core. On the right here, I've shown a couple of pictures of the potential functions in two of the model cores, one for H with 3D, the narrow one here, one with H with 4D, and you can see how these differences between the strength of the nitrogen, the argon interactions and the differences in sizes affect the positions of these minima, the depths of the minima, and the shape of the potential function. And one thing that comes out of this work is the considerable sensitivity there is to very small changes in these potential functions. These are the three pore sizes which I've looked at, 5, 4 and 3. The interesting values in this column are the actual dimensions which the molecules can get into, and over on the far right here are the H prime or the sigma values for argon and nitrogen. And the point here is that argon, the H over sigma is very nearly integer. And so if argon packs as a face-centered cubic lattice into these slit-like pores, this near integer value means that you can get an integer number of layers of the FCC lattice. But you can see that that isn't the case for nitrogen. That's not going to fit so comfortably. The next one. And here is the first of the simulated isotherms. The dotted line along the bottom there is the plane surface isotherm from simulation. And this is for H is 5D, the largest size that I've looked at. The interesting thing here is that there is this sigmoid shape at the beginning of the isotherm. In both cases, it's resolved now because one is on a smaller scale. Notice that this is pressure times 10 to the minus 4 atmospheres. And then below the liquid, the liquid level on the surface, there's a transition which fills the pore. Next one. When we come down to the next smallest size, there's now a very large deviation between the plane surface absorption and what happens in the pore. And you can see now very strongly the effect of cooperation, cooperative interactions between the absorbing molecules. And again, notice that the scale here has gone down by another order of magnitude. We need really quite high resolution to see this shapeless isotope. Next. This is the smallest pore size, H is 3D, and here the transition occurs at a very low pressure. The inset here shows what happens at the very beginning of the isotherm. The box there has been reset in an inset, and you can see the fairly immediate departure from Henry law behaviour, and the transition takes place there. And of course, the filling is up to the liquid layer state in the pores. So it's only 0.8 theta or so that one's filled again. Next slide. Here we now see a couple of isotherms for nitrogen in the same model, and now the scale is such that I can put all these isotherms, or at least these two isotherms together. This, of course, is entirely due to the fact that the nitrogen interactions are much weaker than the argon ones, and so the cooperative effects that cause condensation don't occur at a much higher pressure. Again, for the size 5 pore, the isotherm is type 4, but the difference is that you have this rise in absorption before the condensation takes place. The H is 4D pore is the only one where the isotherm is approximately type 1 in behaviour, and that may be because this isn't resolved on a small scale in that region. There is some sign of the transitions still remaining in this region within the pores. Next slide. And this is nitrogen in the smallest pore, where one sees a different kind of character again from the argon, in that the absorption is much more gradual, but it's similar to the argon in the way in which there's a Henry law region and then condensation here. The pore filling at this stage of the isotherm covers a very large range of pressure, but there is a very this is in a very small pressure region. Next slide. Here I've taken the same data and compared nitrogen and argon in the same size of pore, but I've plotted pore filling against relative pressure, which is something that experimentalists are generally speaking more interested in. And you can see the contrast between the argon behaviour and the nitrogen, and of course it's questionable whether one would actually now resolve this experimentally on this scale, or whether an experimentalist would draw points straight through here and call it a type 1 isotherm. Next slide. This slide shows the singlet distribution function, that is the density across the pore. The triangles is the density distribution on the plane surface, and you can see that no change has really taken place in this first layer, the sharp peak, between the pore with 5D and the plane surface. But what's happening in the centre here is that the nitrogens are fighting for the space. There's about 1 layer difference between that small peak there and this small peak here, and similarly between there and there on the other side of the pore. But there isn't really enough room to form 2 layers in the centre. And this is taken from that part of the isotherm, the nitrogen isotherm, just before the point where the condensation takes place. So that central region then fills up and forms possibly a single peak there. Next one. This is, again, a comparison between the two adsorptives, argon and nitrogen in the 4D pore. You can see that now, in the smaller size, the point at which filling takes place is more or less similar, but you can see the difference again between argon and nitrogen, this very slow region up to complete filling for the nitrogen. Next one. And again for the smallest pore of all, very similar shaping isotherm, but the difference in the actual amount of filling between the two. The lines outside the graph there is the final filling that is reached at higher relative pressure. And I've compared the filling in the filled pores for the different pore sizes here, and you can see that neither the liquid state nor the solid state is really an entirely satisfactory model. The filling is much greater than the liquid state, but rather less than the solid state. And there is some dependency on pore size, as Hensing was mentioning earlier in his talk. These are now heats of absorption, which we can get from the simulation as well. The thing to see here, these 3 lines which are rather jumbled together for the plane surface and the 2 largest pores. There is some enhancement in the heat of absorption in this region in the 4D pore, but the really dramatic change comes when we go down to the smaller size. And what you see here is that it's the intermolecular part of the interaction which is really being enhanced. There's not much enhancement in the zero coverage heat of absorption. Next one, please. Same thing for nitrogen, similar sort of behaviour. Next slide, please. Here I've just compared the zero heats of coverage for the different pore sizes, different absorptives. And the thing to look at is the enhancement of that zero heat of coverage. None of these pores really changes that quantity by a very significant amount, and the enhancement is very similar between the 2 models. So, final slide here. Well, these are some of my conclusions. First of all, isotherms are very sensitive to small changes in the energy, so we have to be quite careful about the potential energy models which we use if we want to relate simulation to experiment. In general, type 1 isotherms are observed if you go down to a small enough resolution see that this is something which is now beginning to appear from experimental measurements. Cooperative effects are very important. The intermolecular interactions, as well as the molecular surface interactions, play a very important part in pore filling. And a lot of the differences that have been seen in this study can be attributed to the difference between the Leonard-Jones epsilon for argon and the Leonard-Jones epsilon for nitrogen. The ability to form commensurate layers across the pore, something which was first pointed out by Diester and co-workers, is really quite a significant factor in determining the shape of the adsorption isotope. That's an interesting observation, and perhaps can be turned to good use in probing pores. The enhancement of heat at zero coverage is very small, but there might be some cooperative enhancement, that is enhancement from the intermolecular interactions. And finally, a speculative point. Obviously, the model doesn't do everything that it should do with respect to experiment. Perhaps graphite edges are an important thing that we haven't thought about modeling too much up to now.
Thank you very much.